Hello, everyone. Good afternoon. It is a real pleasure for me to introduce Melanie Mitchell to our seminar series for the AI-SDM. I'm Coti Gonzalez. I'm the co-director of AI-SDM. So Melanie is one of those very unique, rare researchers that can balance basic science and deep technical issues very well. She is a professor at the Santa Fe Institute, where she studies complexity, AI, and all sort of deep issues on cognitive science. Her work actually has shaped a lot of many questions on AI and has inspired many of us to think about AI more deeply, not only as a pattern matching or pattern recognition tool, but really more as how it emulates humans and how closely we are at understanding how computational theories emulate human processes. Things like recognition, similarity, analogy have been part of her research agenda, which is really inspiring. But also, Melanie is an outstanding science communicator. So her book, she just signed for me, has been a basic book for everyone to read that is very easy. There you go. Thank you, Julie. Very easily reachable and approachable. And if you haven't found yet her podcast, you probably should. She has had a lot of, success in communicating science that well. So today we are in here for a treat on a very interesting talk that we expect to be illuminating and thought-provoking. Please help me join Melanie Mitchell.
Hello, thanks for coming and thanks to Coti for inviting me. Very excited to be here. So I'm going to talk about abstract reasoning capacities in both humans and AI. Let's see. Okay, so Terry Sinofsky, who's a well-known neuroscientist and a pioneer of neural networks from the 70s and 80s, he wrote this interesting paper after a few months after ChatGPT was released. And he said it was like a threshold had been reached. It was like a space alien suddenly appeared that could communicate with us in an eerily human way. And some aspects of its behavior appear to be intelligent, but it's not human intelligence. What is the nature of its intelligence? So this is the question I think that all of us in AI are asking. What is the nature of the intelligence of these systems? And we know that you can throw benchmarks after benchmarks at these systems, and they do well, often better than humans on many of these benchmarks. But and also that every time a company releases a new model, it compares the performance of that model on various well-known benchmarks and compares it to, the previous model and the competing models. So this is really how people in AI tend to measure or evaluate the nature of the intelligence of these systems. But the problem is that benchmark performance is often not very predictive of real world capabilities. So there's kind of a disconnect. We have AI systems that have passed the bar exam, done better on medical licensing exams than human medical students, and many other kinds of benchmark performance, but we don't yet have trustworthy AI lawyers, doctors, what have you. So a lot of people have pointed this out, that AI has this measurement problem going as far as to say that the way we measure progress in AI is terrible, and questions about how we can trust AI benchmarks. So I think most people in the field have problems with using these static benchmarks to test these systems, and many people have said that benchmarking is broken. So some of the problems with benchmarking include, well, data contamination. Is the benchmark or something very similar to it in the training data? It's hard to know for commercial AI systems because we don't have access to the training data. Yeah. There's AI researcher Rao Kampampati has coined the term approximate retrieval, that even if an AI system hasn't memorized a problem and a solution, if there's a problem that it's similar enough to interpolate from in its training data, it can do what he called approximate retrieval without having the underlying general capacity the benchmark is trying to measure. There's many examples of AI systems relying on spurious associations or what are called shortcuts. So a really extreme example of this that I like is pre-large language model, when people were using convolutional neural networks to do image processing. And there was a group who tried to test a convolutional neural network on classifying skin lesions, photos of skin lesions, as either being benign or malignant. And their system was trained on a benchmark of these things and did very well on the test cases until they realized that the malignant skin lesions photos tended to have a ruler in them because the pathologist was trying to measure the size of the lesion. And the neural network, of course, said, yeah, here's a good feature to use for prediction. Mm-hmm. And it got the right answer, but for the wrong reason. So that's what we mean by spurious association, one that's not intended. And typically people only test these systems on accuracy on benchmarks. That's what's reported in many of these cases. But there's other things that we would like these models to have, like consistency. Do they give the same answer every time you ask them the question? Are they robust to small changes in the kinds of things they're tested on? And can they generalize beyond sort of the in distribution cases? And also, is the test actually a good measure or a good proxy for the general capability that it's trying to measure? This is called construct validity in psychology. And it's not always the case that the test really does a good job of measuring the capabilities that it is purported to measure. This is a problem in testing humans as well. The bar exam may not be have great construct validity for the skills you need to be a lawyer. And then there's the problem of anthropomorphism, that people tend to take a test that has been designed to test humans, like an IQ test or something like that, and give it to a machine and assume that then the same kinds of assumptions hold for humans taking the test as machines. And that's not always the case, clearly. If you have a large language model that can memorize huge swaths of the internet, that may not be there might not be an appropriate to test them on things that could have been memorized. So many psychologists have kind of stepped in and said, wait a minute, we in psychology have developed over the last century experimental methodologies for testing these kinds of alien intelligences, where here they're using the word alien intelligence to refer to babies and animals. Okay, so Mike Frank, a developmental psychology a psychologist at Stanford, wrote this paper, Baby Steps in Evaluating the Capacities of LLMs. And he said, imagine first contact with an alien intelligence. So sort of riffing on my previous quote from Terry Sinofsky. He said, can they understand other minds? Do they have the same concept of humans, et cetera, et cetera? And he said that people have, in developmental psychology, have been asking questions for years of alien intelligence of human children, okay, quote unquote. And he proposes that methods from this research can help probe the capacities of LLMs. Similar message came from Anna Ivanova from Georgia Tech and a group from various universities who were proposing that principles of animal cognition can improve LLM evaluations and other approaches to comparative cognition. So this is kind of a mini industry now, trying to translate ideas from cognitive science into AI evaluation. So I'm going to give you 6 principles that I've either abstracted from those kinds of studies or my own studies that I think are really important for rigorous evaluation of cognitive capacities, either in machines or other intelligences. The first is, if you're a researcher, be aware of your own cognitive bias towards anthropomorphism. We all have it. So we might see a picture like this, another picture like this, another picture like this. What do they all have in common? Well, they look happy, they're smiling, right? Well, in the baby, it's probably correct to interpret that as smiling, but in the monkey, that's actually called a fear grimace. It means the monkey is afraid, not that the monkey is happy. And in the robot, well, there's a bunch of actuators and responding to some code that's a result of the robot looking at a human facial expression, and it's not necessarily correct to assume that the robot is actually happy. This is often called the ELIZA effect. Probably most people here are familiar with ELIZA, one of the first chatbots that was created in the 1960s, purported to be a psychoanalyst. People would type in their problems and they would say, oh, I'm not getting along very well with my mother. And it would say, tell me more about your mother. And people would go on like this, and a lot of people were very convinced that ELIZA understood them and was helping them kind of go through psychological issues. So be aware of your bias towards anthropomorphism. Also, this is kind of a common sense one, be skeptical of other people's and your own hypotheses. That's just like science 101, but we don't see enough of it in AI. People in CogSci spend a lot of time designing control experiments for possible alternate strategies like memorization or shortcuts that could produce observed behavior. So let me give you a couple of examples. First from CogSci, and then I'll show some examples from AI. So how many people here have heard of Clever Hans? Okay, maybe about half. So Clever Hans was a horse that lived in the turn of the 19th century in Germany, and was hailed as the first and most famous thinking animal. Okay, so what Clever Hans could do was all kinds of things: count the number of people in an audience, perform various arithmetic operations, read a clock, recognize, identify playing cards, and knew the calendar of the whole year. And in response to a question, he would tap, you can see him tapping his hoof to indicate either a number or the right option in a multiple choice. And back then, the majority of scientists who studied Clever Hans were really convinced that animals had the capacity to think in this human-like way and do all these tasks. But it turned out that it was actually not the case. That a psychologist named Oscar Funst was skeptical and designed some clever control experiments. He found that clever Hans could not answer the question if the questioner did not know the answer. Clever Hans could not answer the question if he couldn't see the face of the questioner. And so what was happening is that the horse didn't have the capacities for math and counting and so on, but he was actually a genius at a skill that's much more important for a horse. That is reading very subtle facial expressions in order to know when to stop tapping. And Funks reported that he himself tried to avoid making any facial expressions that the horse could use to stop tapping, but he couldn't help himself. It was just unconscious. So that was an example, very famous example of a set of control experiments that showed that while the horse seemed to have incredibly good performance, it was actually relying very much on the human who knew the answer to tell it what the answer was. And lots of people have used Clever Hans as a metaphor for AI, relying on its training data rather than having a general capacity. A second example I want to show you is a study of moral reasoning in infants. Okay, so this is started in about 2007. Some social psychologists and cognitive psychologists were looking at how well pre-verbal infants, about 6 months to 9 months old, could evaluate a social situation. And they used this experimental setup that involved puppets that looked like this. So here, I'm going to show you a little video. You see this red circle with googly eyes. And you know, if you put googly eyes on anything, it becomes conscious. So, and you'll see this little puppet wants to climb up the hill. And it's trying, but it can't quite get up there until the triangle with googly eyes helps push it up. So that's called the helper scenario. Then we have the hinderer scenario, where the same thing happens with the little circle, and it's trying to get up, and that mean square comes down and pushes it down the hill. So this is what the babies saw, and they were asked to, choose one of the puppets from either the helper or the hinderer. And in, let's see, come on, I want to go to the next slide. Yeah, they robustly chose the helper over the hinderer. And the interpretation was that young infants can evaluate others based on their social behavior. Okay, so that's a pretty big claim. But another group, having trouble advancing the slide here. Okay, yeah, another group questioned this. They said, wait a minute, is it really social reasoning that the infants are doing, or is there some more simple association that could be responsible? And they asked, well, they noticed by looking at the videos that in the helper scenario, the red circle did a little bounce at the top of the hill. Whereas in the hinderer scenario, there was no bounce. Were the babies responding to the bounce? And so they did a little study where they did a little different version of the task. And here they have a blue circle that has this little googly eyes, but doing the same kind of thing. And we're going to see the hinderer come, and watch down at the bottom, there's a bounce. Okay, and they did these 3 trials: bounce on the top on helper trials, bounce on the bottom on hinderer trials, bounce at the top on helper and bottom on hinderer. And what they found was this. The number of infants choosing each character at the top, almost 80% chose the helper when it bounced at the top. almost 80% chose the hinderer when the circle bounced at the bottom, and about equal for both bounce. So they said, okay, our findings call into question the view that infants enter this world with an innate moral compass. Well, this wasn't done yet. There was back and forth, and this was in the days when you actually, you published in a journal and you saw somebody else's results in a journal and you said, oh, let's experiment on that in our lab. Then they published. And so this takes over years, and there's kind of a back and forth argument about these things where each side is questioning the other side's hypothesis and experiments. So I don't know. I think that the question is still open, the degree to which these whether babies have an innate moral compass. But the point here is that this sort of culture of questioning other people's results and doing careful control experiments to try and see how well they hold up. And in this paper, talking about infant cognition, this author said, infant cognition requires a high level of creativity in the creation and testing of alternative explanations. This is also true of animal cognition, and it is also true of machine cognition, but not the creativity of creating testing alternative explanations is sometimes lacking in AI. It requires replicating and further testing others and your own work. And this is not something that people in AI tend to do very much. Okay, another principle is to not just look at the successes of your system, what its accuracy is on a benchmark, but analyze the failure types that often give more insight than success, and embrace negative results. So this paper from an animal researcher was lamenting the fact that it's a lot easier to publish studies about clever animals than octopi that can reason about space, and birds that can classify cancer from non-cancer, than what she called killjoy explanations, which are those where the cleverness of the animal maybe wasn't so clever, like clever Hans. And she said killjoy explanations are less likely to make headlines than stories about how octopi or birds are unexpectedly human-like. So there's a publishing bias. And people have complained about this in machine learning and said we need to do a better job of embracing negative results and sharing them. And there's even a journal of negative results. Maybe not as high impact as, one of the big AI conferences, but that's where you can go to publish your favorite negative results. Okay. A fourth principle which is often done by cognitive scientists, is to design novel variations. You have your benchmark, but also you should design some novel variations to test robustness and generalization. So I'm going to illustrate this with some work from my own group. This is actually a different group, but this group published a study in Nature Human Behavior in 2023 about what they called emergent analogical reasoning in large language models. And they had 3 different benchmarks that they used. One was I'll explain what they are in a minute, simple letter string analogies. And they looked at some older models back then, GPT-3, and they also did some studies with GPT-4. GPT-3 outperformed humans on average. They used also what they call digit matrix problems, outperformed humans, and some story analogies where the humans were still doing better, but when they tried GPT-4, it outperformed the humans. And they said that GPT-3 and 4 unlike other neural networks previously tested, displays a capacity for zero-shot analogical reasoning across a broad range of tasks. Okay, let me explain to you this letter string domain. This is work done, Doug Hofstadter back in 1985, introduced this domain, and I ended up doing my PhD with him and actually built a system that could solve these kinds of problems back way back many decades ago. But the idea is that you have these simple relational analogies where a string ABCD changes to a string ABCE, and the string IJKL, well, most people will say the L should change to the next letter in the alphabet, which is M, okay? And here's another kind of analogy. Here, a doubled letter like the BB gets moved to a single letter, and so you do the same thing for the KK, okay? And here you have a string with a letter that's out of place, and the same thing in the bottom string, even though the letters are at different locations in the strings. So Hofstadter developed a huge number of these different analogy tasks showing different kinds of relationships. And that's what this group, Webb et al., looked at over on the, I guess, your left-hand side of the screen, and found that GPT-3 was better than humans. Humans were UCLA psychology undergrads. So with very special group. With my colleague, Martha Lewis, we decided to test the robustness of that, okay? And we actually tested robustness on all of the domains that they looked at. But we did this in two simple ways for the letter strings. We said, well, suppose that you live in a counterfactual world in which there's a different alphabet. M and E are swapped in this one, okay? And now do this analogy problem in that counterfactual world. And so we translated the problems of Webb et al. Into this new alphabet world. And we also did the same thing, but with an alphabet, quote unquote, of symbols. So we have a sequence of symbols. And our point was, if you can do analogies in general, you sort of recognize relationships and so on in general, you could probably adapt to these two counterfactual worlds. And what we found is that while humans, in our case, a group of humans on a prolific website, their performance didn't change all that much as we changed the number of letters permuted. And over here, we looked at the symbol alphabet. The GPT models we tested were much worse on these kinds of counterfactual tasks. And so we were then skeptical that these systems had developed a robust kind of analogical capability, at least as shown by this particular task. We also showed similar kinds of variations in their other domains and showed that similarly, in most cases, the models were not robust. So you might say to me, well, okay, GPT-4, that was like so last year. Now we have GPT-5 and we have 5 point whatever we're up to. And those models can do this. But my point is not that, but it's that these kinds of evaluation principles, like show some variations and test for robustness, should be important in any evaluation. Okay. And my fifth principle is to consider what's called performance versus competence. Okay, performance, this is a distinction made in linguistics, psychology, probably some other fields. So performance is how well the system does on your benchmark, say. Competence is how much it has been able to capture the general capability. Okay, so you can have two kinds of situations. You can have your system possess the capability, but can't demonstrate it because the task requirements might be too hard for it. So if I put a piece of duct tape over your mouth and I ask you a question and you can't answer, I ask you a math question, you can't answer, I shouldn't say you're bad at math because I've limited your performance, even though you might have the capacity. But we could also have the situation where the system can show strong performance, but not have the underlying general capacity. So I'm going to illustrate that using what's called the abstraction and reasoning corpus. How many people have heard of that? Okay, fair number, but not everybody. So this is a benchmark that was introduced in 2019 by Francois Cholet at Google, he now has his own startup company. And he wrote this paper called On the Measure of Intelligence, where he was trying to come up with a good way to fairly compare humans and machines. And he designed tasks that looked like this. Okay, so I give you 3 demonstrations of a transformation on a grid. Okay, and then I say, apply the same or the analogous transformation on the test input, which is over on the right here. This one's pretty easy. You sort of see that there's some kind of object, and the object is spitting out some kind of like laser beam type thing that goes all the way to the edge and is the same color as the little square in the base of the little pyramid. Okay, so here's another one. This one's a little harder. Anyone see what the rule is here? Yeah?
Color change.
Color change, but using what rule?
Oh, L's are blue.
L's are blue?
Oh, yeah, so two-sided L's are blue. Yeah, reds are 4 segments.
Yeah.
Pinks are 3.
Yeah, so it's a shape invariance thing where, what you call the L's, they always turn blue no matter how they're rotated or what size they are, and the same with the other shapes. So what these tasks were meant to capture were what Cholet called core knowledge priors, which comes from an idea in psychology due to Liz Spelke that humans are born with certain kinds of abilities, like or knowledge, the knowledge that the world divides into objects, and that objects have certain kinds of relational properties. They have certain kinds of geometry. That space, we know some things about spatial relationships, like some things can go inside other things, some things can go next to other things, and also we know things like some things are bigger than other things, some things are smaller. These are called core knowledge priors. There's a bunch of debate about how innate they are, but that's the issue here, is that they're very simple kinds of relationships like shapes and shape invariance, or something moving, being extended to a boundary. Okay. And so what Cholet said is that ARC is built on this explicit set of priors designed to be as close as possible to innate human priors. It can be used to measure a human-like form of general fluid intelligence, and that it enables fair general intelligence comparisons between AI systems and humans. Okay, so there's a long history between 2019 and 2024 of people trying to build programs to solve ARC tasks and not doing very well compared to humans. But in 2024, Cholet and some other people offered a $600,000 prize for a program that exceeds 85% accuracy on a private test set of 100 tasks. So Cholet published 800 of these tasks and had kept out 200 for private test sets. I'm not sure where the 85% came from. They decided that as their threshold. And it turns out that if you just give an image like this to a vision language model, it can't deal with it. They just haven't, this is so out of distribution for what they've been trained on that they can't really figure out what's going on. So instead, the way that these problems are presented to models is in this textual format where numbers encode the colors, right? So you can see up there these input, output, and then you give a test. Okay, so keep that in mind. In the 2024 competition, the best score, the team that scored the highest with their program was 55% accuracy. Their program used a large language model and some other, what they called test time inference or test time training, but still not at the threshold. Humans were measured to be about 64%. This is again on prolific, and I would take it with a grain of salt. But you know, some of these problems were a little hard, even for humans. But the real story is that OpenAI's O3, their reasoning model, which could not enter the competition because it would take too long for it to run, got a very high accuracy when it was trained on a different private evaluation set. And so the reasoning effort, which is the budget for output tokens during its reasoning phase, low or high, the high got 88%, so higher than that 85% threshold. Again, it didn't win the prize because it was too, first of all, they couldn't run it on their own servers, and also it just took too long. And you can see how many tokens it generated over 100 tasks. So I showed you 2 tasks, right? How many tokens did you generate? I don't know, but over 100 tasks. On the high one, it generated 5.7 billion tokens. many volumes of tokens to solve those 100 tasks. But it did it, and the ARC Prize Foundation said that this is a genuine breakthrough, making a qualitative shift in AI capabilities. But our question was, how are these models solving these tasks? To what extent do they grasp this intended core knowledge versus some kind of alien reasoning? And that's the topic of a paper that is under review right now called Illusions of Abstraction in Contemporary AI, where we looked at a slightly easier data set than ARC, which is a data set that my group made called the Concept ARC data set, in which we explicitly built in the core concepts that ARC was supposed to capture. And these are things that include note concepts like above versus below, horizontal versus vertical, inside versus outside. And we designed 480 of these tasks that were grouped according to the concept. Okay, so here's an example where I'm giving you 3 demonstrations and a test. So anyone see the answer here? Yeah? Well, most people will see it pretty fast. Remove the top and bottom object. Okay, so top and bottom. Here's another one. I don't know if the colors come across so well here, but this one is extract the center square. Okay, so that's the kind of thing. We tried to make them easy for people, and also to isolate as much as possible a concept so that there was only one concept at question. And we evaluated AI reasoning models and humans, and we asked for both the output grid. So the task is to generate an output grid, and that was the task on the original ARC prize. But we asked also, what transformation rule did you use? We asked it to articulate the rule. And we evaluated performance both by asking, is the output grid correct, just like in the ARC prize? But also, is the stated rule correct as we intended? Like, did it say remove the top and the bottom object, or is it using some other kind of non-human-like rule? Is the rule correct, but doesn't capture the intended abstractions, or is the rule incorrect? So let me give you a couple of examples. Well, first, these models did pretty well. So we looked at textual input and visual input. So the textual input is just those integer arrays that I showed you. The visual input was actually giving it images. Okay, and you can see that on the textual input, these are the three models we looked at. O3 did really well. Claude and Gemini didn't do quite so well, but they still did pretty well. Visual input, everything was terrible. Humans got visual input and they got about 73%, so less than O3. But what about the stated rule? So remember this problem. Here's a typical human rule. Use the same grid sizes in the input. There can be multiple objects. Remove the top object and the bottom object. So we rated that as correct as intended. So correct intended. And then the correct over there means it got the correct output grid. Claude Sonnet. Remove the topmost and bottommost colored regions. Keep all colored regions in between. Okay, we said that was correct as intended. Gemini. Okay, these rules get kind of wordy. So this was a weird rule. It said, identify all connected shapes of non-zero numbers. Remember, zero is like black. That's an object. Sort these shapes first by their size in ascending order, then by their color value in ascending order. So it was actually using the color value of the cells, which was not intended to be used in the art prize. Remove the two shapes that come first in the sorted list. So you can actually go through this, and it turns out that this is a correct description of the demonstrations. But it's certainly not what was intended by the task designers, namely us. And so we called that correct but unintended, and it resulted in an incorrect output grid. And then O3 also had kind of a weird rule, which turned out to be incorrect, like it didn't even correctly describe the demonstrations. But this is to give you sort of an intuition for what we mean by these labels, which were manually given by our group. So here on this task, humans select the color that is in the middle of the input, only output that color as a 1-by-1 grid. Okay, that's right. O3 got pretty much the same thing, although the way that it described middle was a little nerdy. It said index floor of n over 2. Okay. Claude Sonnet, again, here wanted us to sort the color values by ascending order. That's according to their coding. And so that was correct, unintended. And then Gemini 2.5 Pro also used a sort of strategy that had to do with these numbers. And in general, here, this is the plot of our results. I'll explain it one by one. So on the y-axis is the percent of 400 of the 480 tasks that in which the output grid was correct. So for instance, here, percent of correct output grids, and here is percent of incorrect output grids. But for each correct output grid, the green is the percent that both the rule was, the output grid was correct and the rule was correct as intended. But the yellow was there was a correct output and a correct rule, but the rule did not capture these like human-like priors. It was some weird Rube Goldberg-like rule that worked, but was kind of using what we would call spurious associations. And it got the correct output by chance, but the rule was wrong, even for the demonstrations. So that's how we showed all this. And what you can see is that in the, well, I'll go back to here. There were about 77% correct grids accuracy, but about a third of those were due to either spurious or even incorrect rules. So these were the right for the wrong reason kind of rules. So this is a high performance, but it overestimates the underlying general capability to reason like humans, which was the goal of the original ARC test. So this is a high performance, lower competence, if you want to make that distinction. But we also see the opposite. Even this is the incorrect grids for O3 on the visual input, but even though it got most of the answers wrong, it got a good percent of the rules correct. So this is a low performance, higher sort of that underestimates competence, because it was actually getting the right rule, but getting the wrong answer, because the vision transformers were having a hard time dealing with like outputting the right grid. Yeah.
Why can't it follow its own rule?
That's a very good question. It has trouble getting the right grid dimensions. That's one thing. And sometimes it hallucinates colors wrongly. I don't know. There's lots of reasons. Yeah.
Do you think they might be coming up with the rule post hoc reasoning, that they're not actually using the rule? It's just, even human can sometimes do it. We make decision and then we justify afterward. But
yeah. Yeah. So what we saw on the visual, on the textual inputs, most of the time when it got a rule, even if the rule was wrong, the output that would generate would follow that rule. So the output was faithful to the rule in the textual domain. In the visual domain, that wasn't the case. And I'm not sure why. And we asked it to generate, we basically asked it to generate the rule and the output at the same time. Or like we said, first generate the rule, then generate the output. And then return, the rule and the output. Yeah.
Do you ask it, could you see its trace of its chain of thought reasoning?
Yeah, so it would output voluminous chain of thought. And we didn't go through all of those to see if they were faithful to the rule, but the ones that we did go through looked pretty reasonable. Yeah. Okay. So we also looked at, there were some rules that we couldn't evaluate because either the rule wasn't generated or the rule didn't make sense. And for the human studies we did, we didn't have the data we used was from actually a different study where they didn't ask humans to generate a rule if the grid was incorrect. So we're missing all that data. But from the data that we have for the correct grids, most of the human, a greater percentage of the humans gave sort of correct intended, and even their correct unintended rules looked a little different. So I'm going to show you that in just a minute. And this was to answer this question. We found that the rules were faithful, the output grids were faithful to the rules, correct or not correct, about 95% of the time on the textual side. So another question we asked is, to what extent do humans and these AI systems, when they generate a natural language rule, do they talk about these core knowledge concepts in the rules? And so what we did was we collected terms from the rules that were related to objects, sort of the one big part of of core knowledge, and terms that were related to grids that were specific to this domain. So we're looking for like more and more abstract terms or very domain specific terms. And so like for the objectness words, the more abstract words, we looked at things like this that tried to describe objects. And for the grid specific words, we looked at words like cell, pixel, row, column, value, etc. And we computed the proportion of rules containing at least one term for each group. And here's what this looks like. If you look at the proportion of rules that contain objectness terms, you can see that humans are talking about objects almost all the time, whereas the models were talking about it much less of the time. And if you look at grid-specific terms, humans very rarely talked about these grid-specific terms, and the models were talking about them much more. So it seemed like the models were focusing on less, at least for humans, less abstract features than the humans were.
Was there any difference in the way that the task was described to the models versus the humans? Like if you have like a human participant, oftentimes you give them like a preamble of like, this is what you'll be doing. And I'm curious if there's like a description of the task that like set the terms differently.
It was a little different, but not much different. I mean, basically we said, here you have these grids and a transformation that's demonstrated in the demonstrations, and you need to transform the test grid in the same way and generate a new grid and a rule. And for the models, we just gave them the, either textual or visual grids, said example 1, input, output, example 2, input, output. So
was there a prompt about like there being?
Yeah, in both cases. Yeah.
Is this for the text-based models?
This is for the text-based models, yeah. We couldn't do that much. And this is only for the ones where they got correct grids. And again, here's for all of the LLMs, for each type of rule, you can see, even when the rules are correct but unintended, humans, the humans tend to use these objectness terms, and models tend to use the more grid-specific terms. Okay, so the take-home message. High accuracy on a benchmark doesn't necessarily mean that the models recognize and reasons with the abstractions intended by the task creators. And why does this matter? Why do we care? Well, in some cases, we want AI to think differently from us, right? We want them to find new patterns to make sense of data. Like, for instance, AlphaFold found patterns that, as far as I know, still no human really understands how it was so successful on protein folding, but it was finding some kind of patterns that humans didn't find in the data. But in other cases, we want AI systems to understand the world the same way we do. Here's an example that I collected where somebody's driving their self-driving Tesla, right? And he's tweeting, "My car kept slamming on the brakes in this area with no stop sign. But after a few drives, I noticed the billboard." So there's like a police officer holding up a stop sign, but it's an ad for something. I don't know what, but humans know enough, most humans at least know enough not to stop there. But this Tesla, this is an edge case, right? It hadn't seen anything like that in its training data. So it stopped. And people are using this kind of on the streets of San Francisco to fool Waymo taxis, and seems to work, I guess. So we need AI systems to understand the world in the way we do, like in a self-driving car, and also in systems that interact with us so that we can assess their trustworthiness, their safety, their interpretability, and so on. And just looking at accuracy alone might mask exploitation of superficial features like I showed, and unhuman-like reasoning. So we really need insight into the alignment of human and AI understanding for predicting how well these systems will generalize in the human world. On the other hand, if you get low accuracy on a benchmark, like we did in our visual modality, that doesn't necessarily mean that the models are reasoning incorrectly. It may be some kind of performance kind of constraint. So my models, my principles, these 6 principles, I think are important. But if you look at number 6, replicate and build on others' results. How many people here have submitted a paper ever to a machine learning conference? Okay, so you might have gotten this kind of review. And this is sort of the review that you get if you replicate and build on somebody else's results, because for some reason, the culture of machine learning is to punish that kind of work. And I think contra to reviewer 2, the hallmark of good science is the replication of prior findings and incremental, quote unquote, extension of prior work. So just to conclude, if you remember from the beginning, Terry Sinofsky asked, what is the nature of their intelligence? And I would say that determining the nature of these AI intelligences or other alien intelligences takes a lot of rigor and creativity, and we need more of that in AI evaluations. And, you know, the Cholet et al. On ARC, if you've been following that work, you know, they said, oh, ARC has been solved, ARC 1 has been solved, the ones I showed you. Let's build a harder benchmark, ARC 2. Oh no, ARC 2 has been solved. Now, just last week, they came out with ARC 3. And I think maybe we don't need necessarily harder benchmarks, but maybe more rigorous evaluation methods. So thanks to all the people who participated in this research, and thanks to you for listening.